Hello everyone, here we are going to start the last part of our series of lectures on the application of machine learning in environmental science. And as I mentioned earlier, in the last part I'm going to discuss a little bit about the recent findings of my own research career as a PhD candidate under the ITN Marie Curie PhD program. The main idea of my research is to explore the potentials of the machine learning in general, and in specific, physics-based machine learning in addressing the uncertainty which is involved in contaminant transport modeling within the subsurface flow regions. To start with, we need to have a brief understanding of what we actually call uncertainty quantification. So, uncertainty quantification, in a very poetic way, if we have a definition about, is somehow combining the scientific and artistic approaches to develop, analyze, and enhance models under uncertain conditions. Uncertainty quantification, or hereafter we call it UQ, is crucial for predictive modeling, which enables quantification of level of confidence we have in the results that we are getting out of our model, which is developed for the system under study. And this understanding of potential variability in the outcomes can be useful in addressing several scenarios that we usually consider in addressing the problem that we are approaching. As a breakdown for the UQ, and if we can call it a qualitative breakdown of the total uncertainty, describing the contributions from data. The data can be noisy or gappy, and this can cause uncertainty. Another aspect that uncertainty comes into the play is the physical models. The physical model can be misspecified or stochastic in essence. Another aspect can be the uncertainty that we have regarding the neural network itself. As we discussed earlier, we can have data-driven modeling to address the system under study. So the neural network itself has an architecture that need to be defined and designed and optimized, which is actually addressing the hyperparameters and also making sure that it's not underfitting or overfitting, and also another aspect which is overparameterization, which is in essence the size of the neural network. Another aspect that the total uncertainty has a contribution from is the posterior inference. So it's just to clarify that here we are not going to into the deep detail again regarding definition of uncertainty, and it's just to give you an overall idea about what is uncertainty and how it can affect the performance of our models. So that would be usually enough to have an idea about this terminology, this area of research, and then we can start to discuss a few results that I'm going to show you from my own research. And here I have designed this infogram that somehow summarizes the points that I've mentioned earlier. So, in uncertainty quantification area, this is a definition that mathematicians have regarding the uncertainty. If we can define mathematically the uncertainty regarding a parameter using the variance of that parameter, and here the parameter is the state variable that we are trying to describe and address using our models, and this model is actually based on some input variables and also some observations that we call it here D or data. And in order to break down this variance, we can have two types of uncertainty. The first one is aleatoric, and the second one is epistemic. Let's see what actually are the differences between these two types of uncertainty. So, aleatoric uncertainty, also known as inherent uncertainty, which is due to variability inherent to the system under study or the process that we are trying to model, such as measurement error or inherent material properties. Aleatoric uncertainty is not reducible by collecting more data. Probably you have heard that in different research areas, that people say that if I had more data, of course, my results would be more accurate. So that accuracy that they are trying to increase, or in other words, to decrease the uncertainty of their results, and by means of getting and gaining more observations, probably using some experiments or some field data, they are actually describing epistemic uncertainty, not the aleatoric uncertainty. So this is just an example to clarify. And these observations, it's often associated with the noise inherent in the observations or stochastic nature of the system being modeled. So this is our definition about aleatoric uncertainty, which is the first part of our definition about total uncertainty. Also, we need to note that this term captures the variability in the model's output due to the variability in the input data. Next part is epistemic uncertainty. This type of uncertainty is due to the uncertainty in the model parameters, which could be reduced, of course, by collecting more data or enhancing our model's fidelity. This reflects our lack of knowledge about the best model or parameters to perfectly describe the process generating the data. And also, epistemic uncertainty quantifies how much the expected prediction, or in other terms, the average prediction, the mean prediction, varies, changes across different sets of parameters, theta, conditioned on the data D, as I have shown here. So, just to visually give you an idea of, again, what are the differences between epistemic and aleatoric uncertainty, here we can see that the distribution or the PDF of the parameters that is describing the model that we have developed for the system under study, which is conditioned on the data, if we plot the probability distribution, somehow you can see that the width of these PDF can be described as the epistemic uncertainty. And in the next part, we can see that this probabilistic modeling approach and the PDF of the parameters of the model, which is conditioned on the data, if we represent them with the samples, it will have an image something like this. And again, here I have plotted the epistemic uncertainty. In the next part, the aleatoric uncertainty is coming to the play. So assume in the previous part, as I mentioned here, we have some observations or samples from our parameter distributions. But for each parameter, of course, we are not 100% sure, right? Because it's a probabilistic modeling, it's not deterministic. So if we assume that each of these samples from the parameter distributions can be modeled by a Gaussian distribution, and if we plot all of them together and we weight them by some coefficients, at the end of the day, we can have the aleatoric uncertainty, which is added to each sample, as I mentioned, via these distributions. And if we, as I mentioned, sum them up, this summation can approximate the total uncertainty by adding up the distributions with their corresponding weights. So here we can see that how the aleatoric uncertainty, by doing some calculations, simple calculations, can add up and next to the parallel to the epistemic uncertainty can generate the total uncertainty that we described in the previous slides. So here we have understood the difference between epistemic uncertainty and aleatoric uncertainty. So just as a recap, the epistemic uncertainty is coming from the model and can be reduced by more number of samples and observations from the system. But aleatoric uncertainty is inherent to the model and cannot be reduced by having more observations. Here we can see that the post-training calibration of uncertainty predictions for function approximation and deterministic PDE problems, and also calibration can be applied using data from the state variable, as I mentioned in the previous slide, at different locations. And for solving stochastic partial differential equations using samples from realizations that here actually we have denoted by the C parameter here, we can see if we are going to compare the classic PDEs and the stochastic PDEs, here by only having some observation from the state variable and also the corresponding uncertainty, this is somehow going to be the way that we are addressing the total uncertainty. But if the model itself has some stochastic characteristics, such as the way that we have defined the aleatoric uncertainty, or in other terms, if the aleatoric uncertainty is also involved and comes into play, we need to address the uncertainty for each realization, or in other terms, different scenarios that the system under study is taking or gaining as the dynamics of the system. So the general take-home message here is that the aleatoric uncertainty is a bit more complex to address and needs more care in order to understand the behavior of system and the uncertainty involved with the outputs of the system that we are studying. So here we are going to actually start the main discussion and how I'm going to use the physics-informed machine learning or physics-informed neural networks, and how I'm benefiting from the versatility of these kind of networks into the UQ. So what are physics-informed neural networks? Physics-informed neural networks integrate deep learning strategies with physical laws. So what were physical laws? The PDFs, the partial differential equations that we have seen some examples in the previous slides. And these pins, in short we call them pins, are embedding the structure of underlying physics directly into the architecture of the neural networks. Don't worry, in the next slides it will be clearer for you. This integration allows pins to not only learn from the data, if we have any, but also respect the laws of physics, ensuring physically plausible solutions. So let's put it in a very simple words. So in a sense, actually it means that if you remember in the first part of the lecture, we were saying that we need both human expertise plus some data and observations. And here is when machine learning comes into the play, specifically if we don't have human expertise or we have the expertise in a partial form. Physics-informed neural networks are actually very important in the domains that we have low data or sparse data, gappy data, noisy data, or even no data. But we have full knowledge about the physics going behind of the system. So it means in the areas compared to the classical machine learning that we were saying, they are very strong in the domains that we have bunch of data. And of course, it would make sense because the neural networks or the machine learning tools, they are going to learn the dynamics using the samples of the data, those pairs of X and Y in the numerical form and in the labels form or in the classification form. We had the input data, the image itself, for example, and the labels, cat or dog. But in the physics-informed neural networks, we can say that there are some problems that it's very hard to gain some data. The data are expensive or they are remote. It's very hard for human beings to get access to, for example, in other planets. But we, based on the physics, Newtonian physics and relative physics, we have some general idea about the physics behind the system under study. So, in these areas, we are not going to discard the physics we know about the system and what we have, nothing, no data, right? Or sparse data. And we know that classical machine learning tools are not good wherever we have low data. So if our budget in terms of data is low, we need to rely on some other sources of information. And this source of information is actually based on the physics. So this is the definition of pins in simple words. So, as I discussed and mentioned earlier, my main goal is to see if I can use these kind of models as a surrogate for the ab initio UQ with these kind of tools. So, probably it looked a bit complex, but ab initio means before we enter actually addressing the systems and approach the system and understand every detail, every bit of the dynamics of the system. For example, assume that we need to design an experiment. In that experiment, we have no idea of the parameters, right? How we need to design, for example, the column, what kind of soil we need, for example, in a column test. My examples are mostly regarding the hydrogeology area and subsurface flow. But you can assume any experimental setup, and it's your first time that you need to design that experimental setup, and you have no idea what are the embeddings, what are the parameters, what are the domains, I don't know, like how big the experimental setup should be, these kind of measurements. But you know the system that is going to you are going to address using that experimental setup, right? So here we can use pins that doesn't need actually data, or you can use sparse data and have a general and pre-information regarding what's going on or what will be going on in the experimental setup, and then you can optimize the parameters of that experimental setup. This is what actually we mean by ab initio uncertainty quantification. So this part will break into several factors. The first one is the input variability. For example, pins can incorporate physical parameters with inherent randomness or variability. So, as I mentioned earlier, this is some sort of aleatoric uncertainty. We are uncertain about the input, and it can involve some randomness or variability, and Ping can address this uncertainty. In terms of stochastic modeling, Pins can solve stochastic PDEs, partial differential equations, that model random processes. And this itself can capture the inherent system randomness and also can address the noisy data. Pins can be a generalized method to solve stochastic differential equations. And it means to infer continuous random processes where we make aleatoric uncertainty actually look like a part of epistemic uncertainty and can be addressed in the post-training phase. So these are a bit detailed for those audiences that actually are not too much involved in the statistics and uncertainty quantification. No worries. It's just important to understand the general idea of this and the message that I'm going to convey in this lecture. But for those who are already involved in this area, this is a very interesting point because we have noticed that we are somehow putting some boundaries between epistemic uncertainty and aleatoric uncertainty. As we understood, epistemic uncertainty can be reducible, but aleatoric uncertainty is inherent, and we can have some general idea about, but we can't reduce it. It's related to the model, it's related to our knowledge and expertise. But here we are trying to somehow address the total uncertainty in a way that both types of uncertainty having the same root, and that's very interesting fact. And also pins can be used for parameter sensitivity analysis. How? Pins can learn how changes in physical parameters impact the outputs and therefore enhance our understanding of the parameter effects under different conditions and different scenarios. In the next slide, we are going to show some examples that it can better clarify the meanings behind all these texts and complex ideas. So, as a part of my own research, I tried to customize the classical or vanilla pins, and I have developed a network architecture that I'm calling it PIN-UU, or the physics informed neural networks under uncertainty. And this model is introduced to solve partial differential equations with uncertain physical parameters. PIN-UU accurately reproduces direct solver results, for example, finite element, finite differences, for multiple parameter realizations. So if you have already heard about pins, the vanilla pins mainly, they were good at solving the partial differential equations. Of course, if we had some observations, that would be much better, but even solely based on physics, it could solve only for one realization. But here we are trying to benefit from pins in a way that it can also address the stochasticity involved within the system under study. And in this network that I have designed in the Polyme, a stage learning approach is employed to overcome some issues, mainly the convergence failures in the optimization problem. So, just to break down in a mathematical form what exactly this means, we can start with definition of a general physical system using the operator f, which is interacting or imposed on the state variable of interest, and that state variable of interest is dependent on the input space, mainly spatial temporal coordinates, and also lambda which is denoted, the lambda is actually representing the physical parameters. And this X spatial temporal domain, as I mentioned, can be a dx dimensional space-time coordinate. And as I mentioned, lambda as the member of the whole group of the parameter space represent a vector of usually unknown, generally unknown physical model parameters. Take it as the parameters that you already wanted to design an experimental setup, and you had no idea what are the measurements, what are the characteristics, geometric characteristics of your experimental design. So this lambda can be denoted, this lambda can be actually representing those kind of uncertain parameters regarding your experimental setup. And this operator F denotes the differential operator, and then the small f is the forcing function that usually in every general PDE we have that. And also this main equation is subject to the following boundary and initial conditions, which has almost the same form, but in a different domain. Usually boundary conditions are in experimental setup, we consider the outer edges, outer sides of the column, for example. So this is just to give you a visualization regarding what we mean actually by boundary conditions. And initial conditions are the parameters or the our state variable, which is defined at the starting point in time in the system within the period that we are going to study the system. And this B operator denotes the boundary initial differential operator, and also again this small b can be the boundary initial function. So in our method, in our approach, we have changed the definition of the problem sets that we are going to approach with using the PIN-UU. And problem sets are classified as neural PDEs when the operator f and beta, which is described in the previous slide, are fully known. So the operators are fully known, or in other terms, the physics involved in the system are fully known. You are aware of what kind of system, either it's advection, either it's diffusion, or in mathematical definition, either it's a hyperbolic PDE, a parabolic PDE, or mixed PDE. Our methodological workflow is specifically tailored to address forward stochastic problems, which means in forward stochastic we have these kind of properties. So as I mentioned, the operators are known, the source terms, boundary conditions, boundary and initial functions are known. State variable, of course, is unknown, and we are trying to predict it. But the difference between forward deterministic and forward stochastic here is that the involved physical parameters are also unknown, which otherwise in deterministic case, we knew actually the exact values of the physical parameters. And the goal is to find the state variable value for all the spatiotemporal points, and also for the all realizations that we can sample over the newly developed space or domain, which is the combination of the spatiotemporal domain, the classical domain, and also the uncertain physical domain, which at the end of the day, it made a new space that we call it omega lambda. So this is the diagram that can show you how we define the architecture of our PIN, which we fully consider the dependency of the network parameters on uncertain or stochastic parameters. And here the KC variable is actually introducing the randomness inside the physical parameters. And we don't have any training points based on the classical definition of training points. And here we are only relying on the collocation points or the samples over the spatiotemporal domain. And here you can see that we are feeding all these inputs on certain parameter space, which can be defined over the desired distribution. For example, take it as a uniform distribution. We are going to sample from that distribution and merge it with the spatiotemporal domain, which of course could be in a 1D problem, it could be a 2D space with X and time. And we are feeding it to the neural network. It's a fully connected neural network. This will be the surrogate that we are going to benefit and exploit within the operators. And at the end, based on the backpropagation strategy of learning in the physics-informed neural networks, we are going to train the parameters that here is denoted by theta of the neural network. And at the end of the day, by solving this optimization problem that we are going to minimize actually, which are the residues of the two equations that I have showed you in the previous slides, we can make sure that the state variable here, that is the direct output of the neural network, can be a good candidate to be replaced for the solution of the partial differential equation under study. So, how we are going to use these kind of networks for the ab initio uncertainty quantification, for example, before experimental design. Physics-informed neural networks, PINs, provide a powerful tool for conducting sensitivity analysis in complex physical systems before actual data collection. This approach is particularly valuable in experimental setups that gaining observation is costly and logistically challenging. So the objective of sensitivity analysis with PINs is actually utilizing the trained network to predict outcomes under various scenarios, or in other terms, parameter setups. For example, in a column test, which is a very general test, typical test in the hydrogeological studies, we may be uncertain about the infiltration rate, the porosity of the medium that we are going to use within that domain, and also, for example, if we are studying the adsorption, contaminant adsorption, we probably have no idea about where we should put the adsorbent layer in order to absorb the contaminants within that column. So the advantages of utilizing PINs is we don't need any direct observation. So PIN can solely rely on the physical laws embedded in the training process, allowing to model, to simulate accurate system behaviors, as I mentioned, without any reliance on experimental data. And also identifying the key parameters before conducting real-world experiments, going out, buying a lot of stuff, and somehow without have any knowledge or expertise, wasting some of those resources. We can do some modeling in order to understand some general ideas about the dynamics of what will be going on into that experimental setup. And in that way, this model helps us identify where parameters have the most significant impact on the outcomes. So therefore, it can also guide us in order to have an effective measurement strategies. So case study here that I have implemented is designing a column experiment, for example. And in our specific application, we are going to explore the contaminant transport through this column and see and assess the impact of an adsorbent layer. And here, PINs or PIN-UU play a crucial role in this pre-analytical phase. So assume the experimental setup. Here, the goal is to understand how adsorbent layer influences contaminant transport across different realizations of the setup. As I mentioned, for example, porosity, varying layer locations, infiltration rate. And as I mentioned earlier, the main impacts of using some ab initio uncertainty quantifications using the type of network that we have developed could be the scenario testing, running simulations with varying adsorbent layer conditions to see how each configuration affects the transport of the contaminant. Also sensitivity analysis, deciding which physical parameter mostly affecting the outcomes, and therefore we can prioritize the variables in the experimental design, and also error rates, as test model predictions against physical residuals to ensure accuracy across all parameter realizations. So this is the simulation that I did as a case study to show you some results about how this PNUU can give you an expert knowledge and some pre-information about the system under study. So assume, as I mentioned, we are going to study the transport of some contaminants. But before that, we need to solve for the flow model. And as you know, in a column test, we describe the flow using the Darcy law. So here I'm not going to describe the details of the system, but the general overview is that we are going to use the Darcy law with some specified boundary conditions, of course, and also with some medium properties, and in two forms. So our medium can be homogeneous, which means it has a deterministic value for the hydraulic conductivity, or even heterogeneous. And by heterogeneous, we means that especially the hydraulic conductivity can be varied over our 2D domain here. So this scheme is showing you the dimensions of the domain, the sort of boundary conditions that we are imposing at this part. For example, we have the infiltration with some specified function, exponential sigmoid function. And here we will have the outlet. These dots are somehow representing the porous media. And the type of boundary conditions that we have imposed. Here we have the Dirichlet boundary conditions, and also on the walls we have Neumann boundary conditions, type 2, and also another type of Neumann boundary conditions, which is actually an influx rate. And after solving for the flow model, we need to use the flow values that we are actually getting out of solving the flow model, and directly use those values within the transport model to determine, first of all, the dispersion coefficient, that is a main layer in the PD that is addressing the transport of contaminant, and the contaminant concentration here is denoted by C. And as I mentioned, this is the advection part, and also this is the dispersion part. So we have assumed some sort of boundary conditions here, we have specified it, and also we have specified the time domain that we are going to have the system under study, and also some relations between the transverse and also longitudinal dispersivity parameters. And again, here we are going to have a Dirichlet boundary condition, fixed concentration, and the rest are actually zero flux. And the type of network, as I mentioned, PNUU, how we are going to adopt that PNUU architecture in order to solve two systems that are interacting with each other, not simultaneously, but one after another. So the answer is simple. Also, we need to use the PNUU architecture one after another, right? So it's not parallel. In other terms, we are going to first use the PNUU to address the uncertainty involved within the our flow model. And here the neural network is going to solve for the hydraulic head for us. And then use the direct output that we are getting in the post-processing phase out of this network, which actually are the vectors of velocity vectors, and we are going to insert it into our transport model and solve for the contaminant transport. So in this way, we can introduce the uncertainty in both phases or in one phase. For example, in the first phase in the flow model, the uncertainty, as I mentioned, can be coming from the heterogeneity of the medium, and also in the transport, the uncertainty can be coming from different parameters, for example, longitudinal dispersivity, as I mentioned here. And this is a uniform distribution. So here we are going to see a few results, and as you can see here in the left part, we have assumed that our medium is a heterogeneous medium, and the distribution and spreading of the hydraulic conductivity values are mainly fixed, but in some regions we have high hydraulic conductivity values. So how it can affect our flow regimes? This will be the change that this high conductivity area can impose to the hydraulic head. And in this plot, of course, it's much clear that you can see the flow velocity is somehow diverging, deviating from somehow central outgoing. If we had if we had a homogeneous field, we can see the divergence here upward, and that's clear because the water goes wherever the hydraulic conductivity is higher, and when we say hydraulic conductivity is higher, it means that it's easier for the flow to pass through that part of the medium. This is the general sense of what we mean by having a high hydraulic conductivity and make our domain heterogeneous. So let's see how the contaminant can transport in the same domain, assuming that we have this high conductivity area. So here you can see that at this point we have introduced the our Dirichlet fixed value as the Dirichlet boundary condition, and we can see the contaminant over time is moving a bit upward. So it's totally following the physics in the flow system, and then smoothly it goes outward here where we had the outlets. Let's see another example and see the differences. So here we have changed the location of our high hydraulic conductivity, and as you can see, the flow velocity is changed in its behavior. So we can see somehow the main players in the defining and characterizing the flow field in the central region. So it's like a diagonal outward flow vectors. So here, of course, we are expecting somehow the contaminant goes a bit directly compared to the previous case that we had some divergence. Here, we are expecting some direct outward movement of the contaminant. And we can see here that we don't have any more that divergence upward, but instead we have this effect here that is we somehow expected before, right? Again, another example, here we are expecting a bit divergence to the right, and the contaminant has the divergence a bit to the right in this area. So this is interesting, and this will be much more interesting if you notice that all these results are coming from a single model, which we called it PUU. Another example, here we can see the divergence a bit upward, and then the contaminant goes out. All right. And another sort of the direct results without any extra post-processing or post-training, we have address the sensitivity of the uh, of the of the variability of the location of this high conductivity area. So assume that the central point of this high conductivity area can change over the whole domain, and we are going to see the variability of the contamination concentration at this point. So assume we have a sensor here and it's observing the contaminant concentration only at this point over time. And we are going to change or play with the location of this high conductivity area. Let's assume that we have like a pin here and we are changing the location over the domain and see how the contaminant concentration is going to vary. So as you can see here, at the specific time of, for example, second 6 or minute 6, it's a dimensionless problem, of course. We can see that if we move the high conductivity area in this region, we can be pretty sure that at this specific time, we will reach to the maximum concentration, right? But if the high conductivity area in other regions, in these red areas or orangish areas and to the black areas, we can say that at this specific time, still, the maximum amount of contamination hasn't reached yet. And this is very important in studying the systems. For example, assume that you have an employer that is hiring you and they are asking you to address how much time we have until the contaminant from this point reaches, for example, to the central point. And based on that time, of course, they need to allocate some resources and do some inhibitive procedures, for example. So if they know, for example, how probable it is regarding that they somehow suspect that they have a high conductivity area, for example, a well that is filled with, I don't know, like gravel, but the whole medium is full of clay. So it means we have some areas in the domain that has a higher conductivity, hydraulic conductivity, of course, but they are not sure about the effect of that of those hydraulic conductivities in the output result. So having this plot, they can easily see that if the high hydraulic conductivity on their map is located here, they probably only have 6 minutes, 6 seconds, 6 days. It depends on the scale of the problem, of course. But if they guess that, okay, the location of wells filled with gravels probably are located here, so they know that they have a bit more time. So this is very important in terms of resources allocation. Another example. So assume that we have put the sensor or observation well here, and again, this result is showing you the variability at this specific time of how much time we need if we play with the location of this hydraulic conductivity area, how much time we need in order to reach the maximum amount of contaminant concentration to the outlet. So if we have the high hydraulic conductivity area within this region, we know that we have more than this time. But if the well filled with gravel is located in this region, we need to make sure that the employer knows that they only have 6.78. Here are another sort of sensitivity analysis, and here we can see the variability of different the variability that different parameters can impose to the contaminant concentration in different times, in different locations, in case that we put the high hydraulic conductivity area or region within the domain. So you can see that we can generate, solely relying on one single neural network, several types of results, and understand and study the uncertainty involved within the system that is caused by the uncertainty that we actually have on the physical parameters involved as a main player into the system of interest. These are another types of plots that can be representing somehow the sensitivity of the maximum concentration amount of contaminant at some specific point by changing the values of DL, which is denoted by DL, and it's representing the longitudinal dispersivity. So, as I mentioned earlier, we can also have some physical parameters even in the transport PDE that is going to change parallel to the or alongside with the uncertainty we have regarding the location of high conductivity well area. Again, another sort of information that these plots can convey to us. And each of these sets of plots can be generated based on the main goal that we are seeking. As I mentioned, for example, the employer that needs us to clean the field, they have very specific goal. They want to know at what specific time, and considering the uncertainty in which parameter, what are the chances that the field still is not contaminated, or under some thresholds it's not contaminated. So based on the goal you are seeking to answer and address, you can generate several types of sensitivity analysis maps. So by this, I'm going to end the last part of my 3-part series of lectures. So as a recap, I have started with an introduction, a general introduction, brief introduction of application of machine learning in environmental sciences. In the second part, we have continued to discuss a little bit in detail the machine learning itself in general. And then in the last part, we have discussed, with a bit, of course, more technicality, regarding the research that I'm involved with, which was benefiting from machine learning in a very special point, in a very special active area of research, which was uncertainty quantification. So the take-home message here is these kind of tools, either relying on data or physics, are very versatile, very useful, and very flexible. And based on the specific need we have as the researchers and engineers, we can manipulate the architecture of these kind of networks, impose the sort of knowledge we have regarding the problem that we are experts, and generate the type of results that we want. By this, I will finish my work. I really appreciate your time and the consideration you put on these 3 parts of lectures. If you have any questions regarding my own research or any general question regarding machine learning and its potential applications in your research area, please scan this QR code. It will directly takes you to my website, and from there, of course, you can easily find different ways that you can contact me. Hopefully, you have enjoyed this lecture as well. Stay well. Take care.